Okay, how's everyone doing? It's Tuesday. And I think we have a short week this week, right? Because July 4th is on Friday. So we're actually halfway through the week. That's kind of nice. What's up, Asta? You have like a number one thing next to your name. What does that mean? Let me see what this means. What? Are you like my number one chatter? I'll give like 4 minutes or something till everyone shows up. Yeah, no, bro. Asta, I'll show it, man. It's kind of interesting. I don't know what this means. You've unlocked something on YouTube. Here, if you want to see it. Yeah, this is what it says. Are you my number one fan? What's up, Sib? Sib is number 2? Wait. Yo. What's going on? No, I think this is like maybe first a comment. Okay, because this is what I'm seeing now. Okay. So I think it's like whoever gets the first comment gets a fun little badge now. Don't worry, there's no points. There's no grade associated with it. Just clout. I think there's XP today for some reason. Oh, what? I guess it only goes to 1, 2, and 3. Each comment increases by 25 XP. What's up, guys? Yeah, I don't know. Maybe something new YouTube's doing. They're always trying to do something new. Competing with Twitch and whatnot. Cool. All right. Yeah. So the most recent homework was due yesterday. I hope everyone was able to find that out. Okay, right? For fluid mechanics. Also, I will say, and I'll make an announcement about this because it is the first homework that we've done. Please check to make sure that your score in Kudu is what you think it is. So, for instance, I'll show you real quick. If we go here to like, Kudu want to load today? Yeah, come on, Kudu. There we go. Okay, Kudu. Yeah, okay. If you go up here to like show my current scores, this is like a dummy account right here, but it'll show what grades Kudu has recorded for your assignments. And this is important because I want to make sure it's getting it right. It will glitch sometimes due to like whatever, if your Wi-Fi is shaky. So I emphasize that. Please like check that as soon as possible. Also, why is this not loading? Excuse me. All right, let's try this again. Can't check your scores if it doesn't load. Show my scores, dog. Okay. Well, that would be a problem. Y'all let me know if you can actually see your scores. I would hope you can. Maybe it's because that's a test account I have running on it, and maybe I don't have scores to show. But you should be able to see like what grade you got on the homework. Yeah, there you go. That's what I'm talking about. For question A on homework 1, I think it says no answer submitted when I submitted and it verified the answer. Okay. Email me if stuff's wrong. I'll fix it. Oh, it actually does work. Yeah, wait. Here we go. Yeah, so here's my score. Yes. So make sure that you're getting the points. Don't worry about the clicker. Well, kind of worry about the clicker stuff. I got to go in and manually have it assign points for participation and correctness. The main thing I'm really worried about is any of the pre-lectures and then any of the homeworks that are due. Try to make sure that you're getting all the points that you should for this. Hey, anything is better than mastering physics. Yeah, mastering physics is absolute trash. Bro, I was tutoring someone yesterday in another physics class at a different university. And yeah, they're using mastering physics, and I instantly just started like raging. I was like, no, dude, I hate this stuff. It's so bad. No, discussion score won't be here. Let me talk to the TA. He should be putting that on Gradescope. Do you see it on Gradescope? you should be able to see your discussion score on Gradescope, I would hope. And then, yeah, this is always something that happens towards the end of the year. I have to merge all the Kudu grades with all the Gradescope grades and then get everything on the Brew and Learn. And I'll make an announcement when that happens, and I'll give you guys like a week to like please make sure that's fine. Like the scores are correct, and because mistakes definitely do happen. Gradescope, okay, cool. Mastering physics is hecka mid. Yeah. So yeah, when we do that, because I had a student email me today from my spring quarter course being like, hey, I didn't get credit for this and my lab TA won't email me back for this credit. Can you like change my grade? And I'm like, no, dog. Like registrar grades were due last week. And once registrar like gets final grades, it's a lot of paperwork to get anything changed. You have to basically like prove to them that it was a serious clerical error. Otherwise they're just like, no. So, but don't worry, that's in many weeks. That's in like 5-6 weeks from now. But just a little heads up, yeah. And little, word of advice when you go into future classes. Try to make sure that your grades are good the last week of class. If your teachers are good enough to grade things. I see some teachers that aren't grading shit, dude, like till like the end of the class, which I think is so wrong. Because then there's no time to contest it. And maybe they do this on purpose, but I digress. Where should I study and solve questions of 1D motion from? 1D motion? Oh, well, that's another class. Wonder. That's Physics 1A. This is Physics 1B. So we're doing waves, and today we're going to finish up mechanical waves. And then later in the week, we're going to go over my favorite topic, sound and music. I don't know. I maybe showed you guys. I was DJing somewhere over the weekend, so I love music. And like math and physics is all music as well, and like it's very fun. Okay, yes, and then we're gonna do sound waves. Yeah. Okay, cool. All right. Again, if you have any other questions, just drop them in the chat. I'll get through them as we go. But let's start off. Welcome to week 2. And then this is gonna be lecture 2, which I think is technically lecture 6, but the naming now for the YouTube matches with the clickers, so we're good. Okay, so in yesterday's lecture, we went over how to derive the equations of motion, right, for a wave, and how to do it in terms of position, and how to do it in terms of time, so, right, spatial and temporal properties of waves. And let me see, what else did we do? We did the properties, the wave equation, the natural frequency due to a rope with tension on it, kind of a lot of like math heavy stuff. This chapter is gonna be a little bit more conceptual. I'm not gonna go super heavy on the math, but what we're gonna talk about is the energy. Yeah, Wonder, you like music? I love music. Music is great. Energy and power of a wave. Okay, so waves carry energy. There are a bunch of different examples of waves that carry energy. For instance, like earthquakes, those are waves, and those carry a lot of energy. They break a lot of things. And microwaves also carry energy. That's what is able, for those of you who are living in the dorm, that's how you eat your top ramen and your mac and cheese, is microwaves, which are transferring energy into water molecules, which then vibrate, and then that heats up your food, and you can eat to, what other type of waves we got? Oh, lasers. Lasers are waves too, right? Yeah, lasers are very powerful and can be used to transmit energy and destroy things, or and then also water waves. Yeah, water waves. They say water waves chew up beaches. That's true. Okay, so in order for radio waves too, yes. I love microwaving eggs in a stainless steel bowl. Oh my God, please don't do that. That's not a good idea. You're gonna have a bad time, dog. There's actually a cool thing. You can create plasma in a microwave if you take, I think it's like sharp points of metal, like aluminum foil, and you put it in there and you microwave it. It does create like a plasma discharge, but you end up ruining your microwave, which is kind of a bad thing. So don't do that. Okay. All right. If we want to talk about the energy in a wave, we can think about, right, waves are vibrating up and down. So there's got to be like some kinetic energy there and some potential energy in there. There is a derivation for it, but we're just going to go straight to the equation that you need to remember, which is that the energy of a wave is this. So don't worry about this. This is like potential and kinetic. This is the important thing. So this is the amount of energy carried in a wave. Mu is related to the, again, the linear density of this is like a mechanical wave, like for instance, like a rope. The important thing here is this. This A here is the amplitude. And then this omega right here, right? This is like the angular frequency. And now if we want to look at what happens to the power, okay, then what we would do is power. This is derived from spring energy. Yeah, it kind of is. In the textbook, they don't really go through exactly where that comes from. And I'm happy to do this during office hours. I can take a deep dive into figuring out like where this comes from. They just say that like this is potential energy and this is kinetic. And I'm like, okay, bro, but like why is it the same equation? Usually we got like mgh and 1/2 mv squared, but I'm just going off of what they give me. This is the main thing. You're not going to be asked to rederive this. This is the main thing they want you to remember. But again, office hours, that's a great time to come by and be like, hey, could you derive this? I'm just curious. Like if you just want to learn physics, like I'm totally down to like take little side lessons, but we also have to cover a lot of topics in 6 weeks, so we can only go so deep during lecture. But good questions. What we also learn about power, if we remember from mechanics, right? Power is equal to like a rate of energy per unit time. It's like dE dt. So the other way to think about this is like energy per unit time. Okay. And if we want to think about the power there, right? The amount of time it takes for a wave to travel, right? Time. This is equal to period, right? So then power is going to equal this 1/2 mu a squared omega squared lambda over period. And we should remember that lambda over period, right? Period is 1 over frequency, right? This is the same thing as lambda times frequency, and this is equal to velocity, okay? So power is equal to 1/2 mu a squared omega squared times the velocity of the wave, okay? And remember that the velocity of the wave doesn't really change very much unless you're going into different mediums, okay? When we talk about electromagnetic waves, such as light or, electric fields, whatever, magnetic fields, this velocity will always end up just being c. So we'll say this like equals c for electromagnetic radiation waves and whatever. But the main thing here is that the power goes as the square of the amplitude and the square of the frequency. Because remember, omega is equal to 2 pi f. So omega squared would be equal to 4 pi squared f squared. So, yeah, really what they want you to kind of remember here is that power is proportional. That's what this means. Proportional means it varies as a squared and omega squared. Everything else usually stays the same. We usually don't like mess with the linear density of our wave, and we usually don't mess with the velocity unless we're changing mediums. So, but this is the key thing to remember. Okay. So, from the power of a wave, right, we can also talk about intensity, okay, which is kind of similar to pressure, right? So intensity refers to like, okay, I have all this power and like, where is it getting delivered to, right? If I have, let's say 100 watts and I'm spreading that 100 watts over, I don't know, like a person. That's a lot of area, right? So you're not delivering that much power to like a specific spot. However, if that 100 watts now gets focused through either like a lens or like a waveguide or something into a very small area, now you do get a very high intensity. And then intensity is what ends up, causing problems for things. If you have very intense amounts of energy in places, things tend to break. So intensity is similar to pressure, which was also kind of, you remember with the needle, right? If I apply a force with, a blunt object, it doesn't really pierce anything. But if I apply a force with a very, very tiny object, such as a needle, now it does pierce objects because the pressure is a lot more. With that analogy, intensity is going to be equal to the pressure, is equal to the power over the area. So in this case, this is power, and this is area. And we should see that this is pretty similar. I always like to draw like the parallels in physics between different things. This is similar to like pressure is equal to force over area. So yeah, just bringing it all back. This is the main thing here. So we'll end up talking about this later when we start getting into sound, because, for instance, if you have a certain amount of power coming out of speakers, like power in like sound waves, then the amount of like intensity, which is like how loud you hear things, will end up dropping off as like 1 over r squared, because the area at which that power of the speakers is now having to cover is the surface area of a sphere. And as you get further away from the speakers, that surface area gets bigger and bigger and bigger. And so the amount of power in a specific area becomes very low. So many P's. Yeah, right? I agree. That's kind of annoying. Because, like, we have pressure, we have density, now we have power. Like, what's up with all these P's, man?
Oh, no.
Oh, no. Yeah. So, again, it's all context, though. So if we're talking about waves and power, know that that P is not pressure and it's not density. Okay. Right. And so, yeah, if we talk about the intensity for like a spherical wave, so we can say for a spherical wave, let's say you have like some source here, which is radiating out power. I don't know. I mean, could even be like a light bulb, honestly, right? Let's just like say there's like some power. Then if we, that's, circle. Yeah, if we were to think about what the intensity is at any point on this surface, we say that like the intensity is equal to the initial power over 4 pi r squared, where r then relates to the distance to wherever, like your radius, wherever, however far out you are. Here we could do like that. There you go. That's like r. Okay. Cool. Good so far? Because next thing we're going to go into is interference. Yeah, reflection and transmission, all that fun stuff. And this is how a lot of things like standing waves happen. Okay, so now we're going to talk about wave propagating through medium and what happens when they hit boundaries. Okay, these are also called boundary conditions, which I don't think you've dealt with yet. You definitely will in E&M. Which we might do we are going to do E&M later in the quarter. I wonder if we'll do boundary conditions. But for sure, if you end up taking more advanced physics classes, boundary conditions become a huge thing, especially in like quantum mechanics. So boundary conditions just say like what happens at the boundary. And here, we'll show a little diagram here. So let's say, for instance, you have a rope here, right? And you're swinging it to like create a wave. I'm sure you've done this with a jump rope before, right? You can like create a wave and you see it moves like a snake, right? Just like moves in this direction. That wave will do different things when it hits the end, depending on what the boundary condition is. So if at the end of your rope, you are fixed at a point. So for instance, let's say this is a rope connected to like a brick wall, and it's like it's glued or something right there. This is called a fixed boundary condition. And what happens with fixed boundary conditions is that as this wave moves to the right, it will reflect when it hits this, but it will end up flipping on the other side and then come this way. So that's what happens when waves reflect off of a fixed boundary condition. You could also think about what is referred to as a free boundary condition. This is, for instance, if you just had like the rope was tied in like a little loop, and then the loop was just around a pole. So it's free to move up and down. In this case, this is called a free boundary condition. And when this wave pulse hits a free boundary condition, it reflects back on the same side. So it doesn't invert. So those are the two different types of boundary conditions you can have, and like what happens to waves when they reflect. Okay. Let's see. They say higher linear events to lower linear events. Oh, that's cool. Okay, cool. Okay. They have, yeah, some interesting things here. If you have like two different densities of waves, that's cool. Or two different densities of strings. Would the ring go up when the wave hits it? Correct. Yes. Yeah. It would. Yeah, it would. Yeah, that's, I mean, and this kind of comes from the right, like, y of x comma t is equal to a sine kx minus omega t, right? What's up, bro? No, you're not too late. What's up? Why does the fixed boundary condition invert and the free boundary doesn't? Oh, okay. You're good, everyone. I believe it has to do with this equation needing to be continuous. Okay? So this describes the function. Do you remember in calculus, like we say like differentiable and then like continuous? Like something is continuous if it doesn't like jump or whatnot, and then something is differentiable if the derivative is also continuous. And also, yeah, they say it has to do with Newton's third law, which is cool. So as the wave, it's for college students, Arun. So as the wave hits the wall here, it exerts a force. The wave exerts a force on the wall, and then by Newton's third law, the wall has to exert a force back on the wave, and that's an equal and opposite force, and that's what causes it to invert. Right? Yeah, conservation of momentum. Cool. Yeah. And so with this one, there is no force being exerted, right, on the boundary condition on the wall or wherever it's connected to, because it's free to move. And so that's why it's able to come back on the same side. Yeah, that's cool. Nice. Okay. So you can also have cases which they say are neither fixed nor free. So you can have something like this. So, and this kind of goes into, you'll probably do this in optics when you have things going from different indices of refraction, like if it's going from a lower index to a higher index of refraction. But in this case, you have a, let me see, let me make sure I get this right. Right, okay. This is low mu, and then this is high mu. Okay, they're talking about like the density of the string. So if you have a wave coming from a low density and then it encounters part of the string that is at a higher density, what ends up happening is you get both. So you're going to get a wave that transmits through that is still on the same side, okay? But then you're also going to get a wave that's reflected back, which is then underneath. And it's because this kind of acts like almost like a wall, right? You're going from lower density into higher density. You can think about like going into a wall is going into like infinite density, right? You're going into the highest density, like the wall does not want to move. So part of it will reflect, part of it will transmit through. It is correct to think about a case where the neither fixed nor free causes the wave to fully disappear on impact. I don't think the wave can ever fully disappear. I guess unless you have something that has like some crazy dampening here to be able to like just dissipate all the energy. Because think about the extreme cases, right? In the extreme case that this has the same density as this, it just keeps moving, right? In the case in which you have a higher density, okay, now you do lose some energy because let's remember that the speed of a wave is related to the square root of ft over mu. So if this mu goes up, you drop velocity. So that's why the wave, once it hits a higher linear mass density, will start dropping in velocity. And as such, it's also going to like lose some amplitude. I think by energy conservation, right? Because right, remember the energy of the wave was related to what was it? A squared omega squared v, or that was the power. But yeah. So if the velocity goes down, I think you're also gonna you are gonna lose some energy as well, which is why your amplitude will probably go down as well. But you're going to then have some amount that reflects back, and that velocity of the wave should be the same as what was happening when it was coming towards it. Yeah. That's pretty cool. But, again, not super important. Really what we want to talk about is interference. Interference is the main thing here. So, we say that waves, yeah, most waves in real life are not simple sinusoidals. They're usually a combination of a bunch of different sinusoidals, all occurring at once. So here, let's pull up what happens when two waves interfere with each other. So when waves interact with each other, you can get like we say, like a superposition. So this is going to be like interference.
Nice.
Okay. 1 second. Let me make sure this is still running. Yeah, good. We're still good. So here we have a wave here traveling this way. Are we going to go over Fourier transforms? I don't think so. I don't think we do Fourier transforms in this. You're free to ask about it during office hours again. So let's say we have a wave here, pulse that's traveling this way, and another wave pulse that's traveling this way. When two waves interact with each other, they're either going to like add or subtract based on like what their amplitude is. So if their amplitude, what is defined as interference? Interference is when you have two waves that interact with each other, two pulses. So in this case, you have two pulses, one traveling to the right, one here traveling to the left. And then as they meet with each other, since they're both positive amplitudes, they're going to add on top of each other, and you get twice the amplitude of a single wave. So this is what gets you, this is what's called like positive interference. Yeah. Okay. Is this like bonding and anti-bonding? Ooh. From like chemistry? I mean, so here's a cool thing. We're learning kind of like the basis of waves. We're going to go over like nodes and like standing waves and like what the allowed wavelengths are. All of this stuff plays a major role when you start talking about quantum mechanics and how to describe wave functions, which then eventually gets into an even higher level stuff of like, yeah, how bonding works, how like electrons are able to like pair with each other with different atoms. That's like a couple like steps down the road. And yeah, I'm not entirely sure about the minutia of like how waves work with bonding, but they are all related. So yeah. Okay. But by the same token, you can also have negative interference. Oh, and I have a cool video. One sec. I found a cool video on YouTube about this. Here we can see it. So here's like a cool little, let's get rid of this, little animation from this guy named Zach's lab. So here, for instance, you have two waves. Do you see these two blue waves that are coming at each other? And then we're going to show what happens to them as they hit. So as they hit, notice how there's a moment where they're like on top of each other and they add together, and that gets you a very large amplitude wave. So here we go. But they pass through each other. So they're showing here that the... Let me turn captions off. How do you turn captions on this? No captions, please. Yeah, here they're showing the light blue is. Let me like get this a little bit bigger so we can see it. So in this case, the light blue is what the sum of the two waves is, and then the green here represents the first wave that was moving to the right, and then the purple represents the other wave that was moving to the left. And so we can see that if we were to add these two together, right, you would end up getting a peak here. So yeah, so that's what happens with positive interference, which is when you have two waves that are both upright colliding with each other. And then they pass through and they keep going. Okay. Now, this can also happen if you have two negative waves. So two negative waves will combine with each other to form a super negative amplitude wave, and then they'll pass through each other and they'll keep going. Now, here's what's cool that happens. Let's say you have a wave that has a negative amplitude, and then you have a wave that has a positive amplitude, and they collide with each other. So what ends up happening is they will cancel each other to create this moment in time where the amplitude is 0. So here, let's try to show this again. Okay, I love animations like this. This is super cool. Oh, we almost got it. I just went a little bit further back. No. There we go. That's kind of what I want. Okay. Yeah, this is cool. So in this case, yeah, you have the green wave, right, which is still trying to move to the right. And then you have the purple wave, which is moving to the left, right? But this amount cancels out directly this amount. And that's why you get 0 amplitude there. Will their interference affect their amplitudes after they move past each other in space? No. They just move past each other. Yeah, there's no it's not like a collision. There's not like a loss of energy. They're just moving past each other. But at that moment, right, the amplitude is 0 because the amplitudes cancel with each other. And this creates what I think we call these antinodes. I always get antinodes and nodes mixed up. One second. Let me make sure I have that right. No, these are called nodes. Good. These are called nodes. Yeah, this creates a node, which is a point of 0 amplitude. I'll explain where this is going to come into play when we start talking about like standing waves. Yeah. which are really cool. So yeah, that's what happens when you have two waves of opposite amplitudes that are coming at each other, and that's called destructive interference. It creates a point where the amplitude is 0. So then here's a cool thing, a little preview for how this works when we talk about standing waves. Let's say, for instance, but what does the amplitude being 0 in that moment do? What's the point? It just means that it's stationary. It just means that the string is not moving there. So watch what happens here. If you have two opposing waves that are coming at each other, but they're like, for instance, out of phase by a certain amount, right? Exactly 180 degrees. Then what happens is, as they collide at different points, this is always going to create these 0 amplitude spots, which are called nodes. And then in between that, directly halfway, it's going to oscillate back and forth between the maximums, and that's the positive interference that happens, and those are called antinodes. So here, maybe like showing the animation again. It's really cool. I think this is really cool. This happens. So watch, they meet here right at the center. This creates a 0 point, okay? And then this purple wave is going to continue moving through until it lines up with the positive face of the green wave, and that creates positive interference. Here it's going to create positive interference here in the negative direction. And then as these waves move past each other more and more, they start lining up with like further peaks away from this center point where they first collided. And then this creates what looks like a stationary wave. Like, it looks like the wave is not moving to the left and to the right. It just looks like it's oscillating up and down. And these are called standing waves. So, yeah. Very, very cool stuff with that. Let's see. Okay, so you can also have superposition of waves that are at different frequencies, and this happens a lot in signal processing, and just like everyday stuff. So, let's say, for instance, you have two waves here. Let's say we have wave 1, which is, this would, for instance, be like a low frequency wave, right? And then you have wave 2, which is a high frequency wave. And then you have the resultant. So this is wave 1 plus wave 2. So if the timing of the meeting is not right, meaning not solely constructive and destructive, will the standing waves still be produced? No. Yeah, no, that's the key thing. It won't be produced. And we'll go over that when we get into standing waves. But what you would end up having, you just have like garbly mess. It's just like noise. So here, for instance, you have a low frequency wave and a high frequency wave, and they're on top of each other. And so what happens is this oscillation, right? This like red oscillation will add and subtract from the blue one to then give you this when you add them together. So you can think about it as, you know, at every single point, I'm going to add, okay, well, this is positive on top of positive, so that must equal like really positive. But then this is negative on top of positive, so this must depress it down. And so what you can see is that you have like an outline of the overall blue wave, but then you also have the red wave superimposed on top of it. And that creates your final signal here. If you ever do like experimental physics and whatnot, whenever you're taking data and analyzing signals, your signals usually look like this. And we think about this stuff as being like noise. This is like what we call like high frequency like noise. Because there's all sorts of things. There's cosmic radiation. There's electrical outlets that aren't grounded. There's a bunch of things that create all this like high frequency stuff on top of maybe what you're trying to measure, which would be this blue wave. And ways we can get rid of that are by doing, yes, FFTs, like fast Fourier transforms, and then doing band passes and all sorts of like frequency filtering. But it all comes down to this, is is that your resultant vector, like the signal that you measure in the real world, has a bunch of different frequencies all kind of on top of each other. And we have mathematical and engineering and cool coding ways to separate this like jumbly signal into its little component parts. It's really cool. So anything related to time, period, frequency, velocity has to be specific for standing waves to be produced. Yeah, standing. Where we'll go over this. Standing waves require like certain characteristics to be true. But yeah, this is for like experimental. My PhD was all this. My PhD was measuring very messy signals, and then doing all this fancy coding, filtering stuff to try to extract out, sometimes you're looking for the high frequency wave, and this low frequency, for instance, is like the 60 hertz of an electrical outlet. Like, so AC circuits in like, the plugs you put into the wall, they all operate at 60 hertz. And sometimes that 60 hertz wave will leak out into your signals that of whatever you're trying to measure. And so if you're trying to measure high frequency, radio waves or something, you might see there's some like 60 hertz like big thing that's moving my signal up and down, and you can filter that out to just get the high frequency part. But yeah, it's cool stuff. Okay, is this how some apps can reduce noise? Exactly. Yes, Amidai, you were totally right. So I don't know if have you guys seen stuff where they're like, if you have a song and you want the vocals, for instance, and they want to remove all the instrumentals, how that works is the vocals, like the human voice, occurs at like certain frequencies. I think it's around like 700 hertz, probably up to like 3 kilohertz. Whereas things like bass lines, drums, all those low percussion instruments, those all usually happen below like 500 hertz. And so what you can end up doing with like a sound signal is you can go through and just like chop those out. And doing that kind of like preserves the vocals. Although, as we'll go into in the sound and music chapter, those bass elements still do have upper harmonics that hit in the higher frequencies. They're just at lower amplitudes. So even if you do like a filtering thing to like get rid of the instrumentals, you'll notice you can like kind of still hear like echoes of it. And that's because the higher frequency harmonics are still present in the signal. Other countries use 50. Yeah, 50 hertz. It changes, right? In America, I think we're 120/60. And so 120 volts, 60 hertz. Yeah, in Europe, maybe I think it's either like 220 or 230 volts. And then maybe they run at 50 hertz. This is also why it's very important that you have the right power adapter whenever you go to different countries, because their electricity runs at different voltages and frequencies. And if it's not matched and whatever your power adapter can't adjust to that, you end up frying stuff, which is not a good time. Yeah. Okay. Let's look at like some phase shifting things. This is cool. So we talked about how like you can have waves that have, for instance, different frequencies and different amplitudes and what happens when you add them together. You can also have, this is called like different phases. Okay, so like different phases. And so this is what we're going to talk about with the standing waves. So like with different phases. So for instance, here they talk about there's a red wave and you can't see it, but there's also a blue wave. And this delta phi here is telling you what the difference in the phasing is between the two waves. Remember that the phasing in our equation, right? It was like y is equal to, I don't know, like a sine omega t plus phi. Let's just do the time dependent one, right? This term here acts like a shift to the left and to the right. Oh, they're doing it in terms of position. Okay, fine. All right, we can do this as well. So we're going to do kx plus phi. So this is like a horizontal transformation of a wave. And depending on what that is, that'll move this to the left and to the right, okay? What we're saying is that when the difference between those waves is 0, when you have 0 phase difference, now these two add on top of each other, which is why the black here is the resultant wave. You get a very big wave, okay? So here we say this is equal to the red plus the blue. Okay, but now look what happens. Let's say instead of them being lined up with each other, that this has a phase difference of pi over 2, which is the same thing as 90 degrees, okay? So that means we move it back a quarter of a wavelength, all right? Doing that, now you're going to start getting some interference, right? So, for instance, at this position, okay, I have positive and positive, so that creates like a bigger amplitude. But here, for instance, right, now you have like kind of positive and like kind of negative, and so they cancel each other out to create like a null point here, a 0 amplitude. And then what you can do is that if your wave goes from being completely in phase to being 180 degrees, which is pi, which is half a wavelength out of phase, now these two add up to a flat 0. Okay, so now you have 0 amplitude, and this is where you have now there's no wave at all. This is also how noise canceling headphones work, by the way. So if you've ever had like, I don't know, like AirPods or Bose, whatever, and they have what's called ANC, active noise canceling, they have microphones built into your headphones, and they're listening for the sounds outside. And if there is a constant drone, like for instance, if you're on an airplane or you're on a bus and like something has like this constant whine or this constant tone, it will record whatever that frequency is that it's hearing. It will then shift the frequency by pi radians, by 180 degrees, and output that to cancel out the sound that you're hearing outside. So it only really works with noises that are constant. If you have things where the frequencies are changing all the time, such as like, you know, speaking, or, you know, like a concert, noise cancellation doesn't work very well. But if you have something where it's pretty predictable, where whatever the sound pattern is pretty constant, again, airplanes are great because like engines always make like a certain whine at a certain frequency. Your headphones will then take whatever that frequency is, identify it, they'll shift the phase by 180 degrees, and they'll replay it in your ear to cancel out the sound from outside. And that's why it's like you don't hear it. It's really cool. So yeah, and that's how you get like 0 amplitude. And then, yeah, you can have like 3 pi over 2, and you see like now things are, yeah, again, adding in some places, subtracting in others, and yeah, it's pretty chaotic. So yeah, that's how interference works with phasing. Okay, now let's think about standing waves. Standing waves are very cool. So let's say, for instance, you have that's tough. Bose is better than Beats, though. Are they? I like Bose. I have, yeah, Bose is, you know, it just works. You know, it's not a bad brand. And then yeah, their Quiet Comfort 2s, whatever, those airplane ones are like super nice. Is positive interference relevant to transparency mode? Because it seems like enhanced version of hearing. Yeah, so with transparency mode, all they're doing is they're listening to what is outside your headphones and they're just piping it in. I don't think they're creating well, I guess, yeah, it is positive interference in a sense, I guess, because you're hearing, because what's outside is still trying to come in your headphones, but you're also hearing like the speaker version of it as well. What is mathematically the difference between shifting pi radians versus deconstructive waves that keep having amplitude? So they're the same thing, right? If you have a wave that looks like this, right? and then I shift this by like pi over 2, okay? So this would be like sine kx, let's say like plus 0, right? 0 phasing. And then we could say plus sine, but then I need this to be, let me think how I want this. I need, yes, hearing aids work the same way as well. Yep, totally true. One sec. I need to do this correctly. This is, because lambda, okay, equals 2 pi over lambda. So then lambda equals 2 pi over k. And I want to shift it by half a wavelength. Yes. Okay, so this would be kx plus pi over k, I believe. Yeah, it's super awesome. Yeah, it's pretty cool. K is 2 pi over lambda. Lambda is 2 pi over k. Yeah. Okay, this is what it ends up looking at. It's like k, and then it's x plus pi over k. I want to say is this. Okay, let me get rid of the k. I don't want to deal with k right now. I'm just going to do it this way. Okay, I'm mathematically I'm losing this on my top. Okay, let's just say it's like sine of x, okay? Versus you have sine of x plus phi. You're phasing, okay? If that phase difference is equal to pi, right? Let's say it moves 180 degrees back, then this is equal to sine of x plus pi. And sine of x plus pi, if we remember from like our trig identities, let me get them for you. Where is it? Here we go. Yep. So sine of an angle, sine of something plus pi ends up equaling negative sine. So what happens is this whole thing becomes negative sine of x, and that's why this thing cancels out with this thing when the two waves add on top of each other mathematically. Yeah, it's if the phase shift ends up being 180 degrees. But it also then, if there's numbers in front of me here like k and x, I forget. You got to like pull one out and then rewrite things around a little bit. Yeah. But this is where it comes from, is that this is the 180 degree phase shift. Yeah. All good. Cool. All right, we still got 20 minutes. We're doing okay. Okay, let's say, for instance, that I start sending waves, okay, towards a barrier, right? And let's say it's fixed, right? I know if it's fixed here, right, that once it hits, it's going to then produce a reflected wave that comes back, right? And then once it hits here, it's going to bounce again and start moving this way. So here's what we can think of. Let's say that I start sending a couple of these waves, right? And I start sending them at a certain rate, okay? So let's say, for instance, I send it this way, it hits, turns into an upside down wave and starts coming back. But then let's say I also send this one. And then I send another one, right? And I keep sending them. So I have a rate of waves that are coming this way and a rate of waves that are coming this way, right? What ends up happening is you're going to start having positive and negative interference at certain distinct points. If the rate at which you're sending these things is a nice like integer multiple of like half a wavelength. You start getting where the top ones start lining up with the bottom ones, and this creates a standing wave. This is, again, kind of similar to what was happening in this video, where we had like two waves. You can think about like the positive and negative ones. And as they interact, they start, if they're lined up correctly, you're going to start having points where the wave doesn't move and other points where it oscillates between between the max and the min. And so, yeah, it has to do with, you can think about these waves going back and forth, reflecting, which means like they're going on the top, they're going on the bottom, blah, blah, blah. And if the rate at which that's happening lines up nicely, you start getting a standing wave. In the case of having fixed boundaries at both ends, okay? So let's say, for instance, you have a fixed boundary at both ends. This is the same thing as, for instance, like a guitar. A guitar has, like, the string is fixed where you're, like, pressing your finger, and it's also fixed, like, on the bridge. These end up being what we call, like, nodes, right? So we know that the amplitude of the wave here has to be 0, okay? There can be certain multiples of wavelengths that can fit in between these two nodes. So, for instance, you could have this be your standing wave. So you could have this and this. This is called the fundamental frequency. Or the fundamental like standing mode that can fit. And let's consider if this is a length L. Let's say this is a length L, okay? That means that you have 1/2 of a wavelength, right? Because a full wavelength would be this. This would be a full wavelength. It's not the first harmonic, it's the fundamental. I believe the first harmonic is the next one up, is what we think. Yeah. Let me see, one second. Next two tones. Do they call this the first harmonic? Oh, they do call it the first harmonic. Yeah, okay, good. All right, cool. It is, yeah, I thought it was, I always get, this is a thing in like computer science. Like, do we start at 0 or do we start at 1? I'm like, where do we start counting? Yeah, okay. They call this the fundamental frequency. They also call this the first harmonic. Okay, fine. To me, like, I think of it in, like, the cello sense of, like, my first harmonic is one above the fundamental. But, okay. For physics, because this is not a music class, the fundamental frequency is the first harmonic. But, yes, so this ends up being what half a wavelength would be, is equal to the width of your, between your two endpoints, between the two nodes, right? Because this right here would be like a full lambda. So we only have half of one. Okay. And then it turns out, right, if that's equal to lambda, right, then do I teach chemistry? I don't formally teach chemistry. I do know a lot of chemistry. So we remember, right, that v, so the velocity, is equal to lambda f, okay? And if we assume that the velocity is the same for all our waves, because remember, velocity just depends on the medium. Oh, Aditya, oh, not today, in office hours later. This is strictly a physics course, Aditya. So v, right, is always equal to the square root of ft over mu. So we say that f is equal to v over lambda, right? So in this case, if half, oh, you're just asking? Oh, yeah, no, it's okay. Yeah. half a lambda is equal to L, that means that lambda is equal to 2L. And so you get that this first frequency, F1, is equal to V over 2L. Okay. So this is called the fundamental frequency. Now, there's another case that I could fit a wave here, a standing wave, in which my endpoints are at 0. And that's called the second harmonic, right? And so the second harmonic happens like this. Okay? Let me draw this a little better. So this is now a node, okay? And for that one, right? This is the second harmonic. Now you have a full wavelength is equal to L. So it has to be in half wavelengths, correct. In the case that it's closed. When we go into the sound and music chapter, we're going to talk about situations where you can have one closed, you can have one open, and those do different patterns. But for now, for the simple case of closed on both ends, you can only have half wavelength multiples. And in this case, right, yeah, lambda, the wavelength, is now, the length of this cavity is now a full lambda. Before, the length of the cavity was half a lambda. Now we're fitting a whole lambda in there, okay? So F is equal to, again, in this case, V over L. Look at the difference between this and this. This F2 is equal to twice F1. So when we count the number of nodes, do we count the number of the middle ones or also the side ones? I think you also count the side ones. I want to say you do. Yeah. Yeah. Yes. How I end up always remembering this, right? Because you see how this is F2, and you're like, wait, what's the 2 thing about this? The 2 thing about this is that there are 2 antinodes. These are antinodes, if you want to remember it that way. Yes, we're gonna do the clickers right now. Sorry, I just wanted to get to this. So this here has 2 antinodes, whereas this has just 1 antinode. But then it turns out you can just keep trying to add more and more wavelengths inside. So these are the allowed patterns, and it goes up and up and up. So this is the higher harmonics. Yeah. And again, it has to do with if you're transmitting waves in and then they're reflecting back, and then it's, there's a rate at which that happens. Depending on how fast you're doing that, you end up getting a higher number of wavelengths that can fit inside that cavity. The fact that this is quantized, do you see how this is n equals 1, n equals 2, n equals 3, n equals 4, right? You're not allowed to do 3.5. You're not allowed to do 4.2. Only integer multiples of half wavelengths are allowed to fit inside 2 cavities like this. Good. This does remind you of chemistry, right? These are quantum numbers. So when you take quantum mechanics, you will learn that the energy levels, because what you learn in quantum mechanics is called the infinite potential well, which is, you have something like this. Here, let me just draw it real quick. So this is called some V equals infinity. And you have electrons that are trapped in a well, and they can either exist in certain certain energy levels. And the energy levels refer to these same standing waves. And yeah, this is how chemistry works. Chemistry talks about electrons in higher energy states. It has to do with the simple case of having an electron trapped in a well of potential, and it's bouncing back and forth, and what are the natural resonant frequencies that can occur at. Yeah. These are the building blocks for quantum mechanics, and then that becomes the building blocks for P-Chem and all sorts of other chemistry and other fun stuff that's going on. So, yeah, the hydrogen atom is a beautiful example of this. On a guitar, all harmonics are there? No? Yes. And we'll talk about this when we do the sound and music chapter. But when you pluck a guitar string, you end up triggering not only the fundamental frequency, but you end up triggering the overtones as well. And that's what gives instruments like different, like we call them like timbre, which is like different like color, different flavor, is how these other harmonics resonate and at what strength they resonate. And it depends on the geometry of your system. Yeah. Pretty cool. And yeah, we'll go over the free one when we do sound and music. We'll do that one. Yeah, that's the node anti-node one. Okay, cool. Here, yeah, let's do some clicker questions real quick. So if you go to where are we at? Ding ding. There we go. Lecture 6 clicker. Oh, I only put 2 questions here. Nice. Okay, excellent. We love this. Okay, first question is to increase the intensity of a wave by a factor of 50.8, what factor should the amplitude be increased by? And then here are the answer choices coming up. Okay. So let's remember from before that intensity is proportional to amplitude squared and omega squared. Okay. So what I always like to write this out. I'm like, okay, well, I1 is equal to A1 squared omega 1 squared. And then another one, right? Let's say like I2 is equal to A2 squared over omega 2 squared, right? I need the intensity to increase by a factor of 50.8, all right? So I say that I2 is equal to 50.8 I1. This is how I say that this has to be increased by a factor of 50.8 of its original. So now looking at this, you get, okay, I1 over 50.8 I1. So I just wrote it out for one situation. I wrote it out for another situation, and then I divided the two equations by each other. This is going to be A1 squared over A2 squared, omega 1 squared over omega 2 squared. And we're going to assume that the omegas are the same. We're going to assume that we're not changing the frequency. So let's say like omega 1 equals omega 2. That means that this is going to go away. Okay. And then this goes away, which is cool. So I get 1 over 50.8 is equal to oh, this should be squared, sorry. Is equal to A1 squared over A2 squared. And so now you can come up with an equation for this, right? So you get A2 squared is equal to 50.8 A1 squared. And then you want to square root each side because we're dealing with A squareds. I don't really care about A squareds. Let's just square root everything. And you end up getting that A2 is equal to the square root of 50.8. So if we pull out our calculator, where'd you go? There you are. So square root of 50.8 is going to be 7.13 A1. And now here's our relationship. It says that our new amplitude, A2, must be 7.13 times my initial amplitude. And so the answer there would be C. And you can kind of see this, right? If I'm trying to increase this by 50, this needs to only go up by the square root of 50 because it's going to get squared anyways. So one way to identify it is you can just kind of see the trick, but for people, I say if this is new to you, and this is a very important concept in physics, to be able to determine like if this goes up by this factor, how much does this go up by? You can also just do it this way. Are calculators allowed in American schools? Yeah, they definitely are. Yeah, at the upper level physics classes, not so much though. Like, you'll do everything in terms of variables here. Okay, so this answer should have been C. Correct. Nice. Okay, good. We got that right. Good. Love that.
Perfect.
Okay. Let's try to do question 2 here. And then let me get the answers for you guys. Says ultrasound of intensity 1.5 times 10 to the second watts per meter squared is produced by the rectangular head of a medical imaging device measuring 2.43 by 5.57 centimeters. What is its power output? Okay. So from before, remember that intensity is equal to power over area. Okay. And the intensity we know is 1.5 times 10 to the 2. Sorry. Yes. Yeah. Yeah, the reason for this, right? So intensity is power over area. But power is proportional to amplitude squared, omega squared. These A's are not the same. I know that's confusing, right? Not a dumb question. We're also assuming here, Cameron, that we have the same area. Yes, you are right. So, in fact, intensity is proportional to amplitude squared, omega squared over area squared. That's really what we should be saying. But the area is the same. We didn't say anything about area. Correct. But you're correct, Cameron. Yeah, no, that's a good thing to bring up. Okay. So I is equal to P over A. So we have 1.5 times 10 to the 2. No, good question, though. Good clarifying. Okay. Is equal to the power. So I don't know the power. So that's P. And then over the area. Okay. But they give me it. They say it's a rectangular device of these dimensions. Okay. So A, area, is going to equal to length times width. So that's going to be equal to this times this. But you got to be careful here. This is given in centimeters, whereas our intensity is in meters squared. Okay. So I need to convert these things to meters first. So that's going to be 0.0243 times 0.0557. Okay. So let's get an area there. So we get 0.0243 times 0.0557. And this gives us 0.00135. And we're going to put that down there. So then if we multiply that by 1.5 e to the 2. Cool. We're going to get that power is equal to 0.203. And then this is watts. Because remember, this was in meters squared. This is watts per meter squared. So when we take this and multiply it through here, meter squareds cancel. And you're just left with watts. So final answer should be choice B. Let's see if that's correct. It is. Nice. Cool. We did it. Great. Okay, cool. All right. That's about it for lecture. Yeah, I'm glad we got through almost everything. Yeah, we got through pretty much everything today, which is good. You're from India, they don't let you use calculators? Well, good for you. I say, not using calculators is a great way to train your brain how to do mental math stuff in your head, and that's useful for so many other things. So it's a blessing, not a curse, don't worry. Okay. That's end of lecture today. So our next lecture will be tomorrow, same time, same place. I'm going to release a new chapter then, because now we're going to go into sound and music. So be on the lookout. That'll get released to Kudu later today. And then just remember that the pre-lecture questions for that are due 2 days from that. So they're going to be due on Thursday by 2 o'clock. Yeah. Yeah, very welcome. Okay, awesome. Yeah, come on by office hours later today. It's at 4 o'clock, so that's in about 2 hours and 15 minutes. If you have any questions about this, you want me to go derive some other cool stuff, happy to do it. I'm glad we got through all the things here. And if things are making sense, ask on Campus Wire. Come on by office hours. I'll help you out. All right, you're very welcome. Enjoy the rest of your Tuesday. We'll see you tomorrow.